Today, I'm going to walk you through my laboratory activity for multimedia processing. I have divided the work into two main sections. Part A, where I process audio signals using Librosa, and Part B, where I handle image processing using OpenCV. Let's get started with the audio. First, I import Librosa for the analysis. Here, I'm loading a sample trumpet sound. I use the parameter SR is equals to none inside Librosa load to preserve the audio's native sampling rate. Then, I visualize the waveform using WaveShow. This plot allows me to verify the amplitude or loudness of the trumpet signal over time. Waveforms only show loudness. To analyze the frequency, I calculate the short-time Fourier transform or STFT. I convert the result to decibels using amplitude to dB because human hearing is logarithmic. When I run SpecShow, I generate a spectrogram. This heat map displays frequency on the y-axis, allowing me to visually track the pitch of the instrument. Now, I want to process the signal. I define a custom function here called Butter Low-Pass Filter, which uses the Butterworth design. I set my cutoff frequency to 1000 Hz and apply the filter to my audio data. This effectively acts as a muffler, passing the low frequency but blocking the sharp, high-pitched notes above 1000 Hz. Moving on to Part B, I switch to using OpenCV. For signal processing tasks like this, it is much more efficient for me to work with single intensity channel, black and white rather than full color. Just like with audio, I want to analyze the frequency of this image. I use np.fft.fft2 to perform a 2D fast Fourier transform. I apply a log transformation to the magnitude because the range of values is too large to visualize otherwise. The resulting plot shows the frequency distribution. The center represents smooth areas and the edges represents details. Next, I apply a Gaussian blur. I use a 9x9 kernel here, and this function averages each pixel with its neighbors. In signal processing term, this is a low-pass filter for image. It smooths out the image by removing high-frequency edges and details. Finally, I simulate a restoration problem. First, I intentionally damage the image by adding random Gaussian noise. I use np.clip to ensure the pixel values stay valid. To fix this, I apply a median filter using cv2.median blur. I choose this over a standard blur because the median filter is excellent at removing noise without blurring the sharp edges of the object. As you can see in the final plot, the image is successfully denoised. That concludes my explanation. I have shown how I can visualize signals, analyze their frequency using Fourier transform, and clean them up using filters.